Welcome back to part 2 of sequences and series in chapter 10. We're in our first lesson. And now we're going to talk about the second part, which are the series. The series they use the sequences, but they sum up the parts. And they take them, and so sometimes you have to figure out what they all are, and then you can just add them up. Sometimes you can follow a certain pattern. Sometimes they're given to you, or as I said, you have to calculate them. But what's interesting is this series can be finite or it can be infinite. And you're thinking, how can I have an infinite sum? I've got to have, if I'm just going to add them up. But it exists. We'll talk about that. There's something called the nth partial sum, which means if I want like the fourth partial sum, that means you're going to add each term up to the fourth term. So if you want the fifth partial sum, you're going to get the first term plus the second plus the third plus the fourth plus the fifth. And if you want, so you have to write all of them out and then you just add them up. If you have a explicit formula, then sometimes you could put that in y equals as the function. You can go to the table and get the values. That's fine. But as I said before in the first video, sometimes it's just as easy to plug in the values and get each term and then add them up. And you can check it on the calculator if you'd like. Let's go ahead and try this one here. We're going to find the fourth partial sum of this function. A sub n is negative 5n plus 3 over n. It's not very hard, but let's go ahead and plug that in. So the first term would be negative 5 times 1 plus 3 divided by 1. That would be negative 5 plus 3 is negative 2 divided by 1. The second term, so we're going to plug a 2 in for n. So we're going to have negative 5 times 2 plus 3 divided by 2. That's negative 10 plus 3 is negative 7 divided by 2. I'm going to go ahead and leave that as a fraction. You can make it a decimal if you'd like. That may be easier for you. Third term. So we have negative 5 times 3 plus 3 over 2. Negative 15 plus 3, negative 12 divided by 2, divided by n. That needs to be a 3. Let me back up. So negative 15 plus 3 is negative 12. Divided by 3 is negative 4. Almost messed up there. All right, plug in the 4. So I got negative 5 times 4 plus 3 divided by 4. That's going to be negative 20 plus 3, negative 17 divided by 4. I'm going to leave it that way. Then, when you sum up those numbers, you can either do that on the calculator. You're perfectly capable of adding that up yourself. Then you're going to find that you have a negative 13.75. Or you could say negative 13 3/4. Doesn't matter if you used the fractions. But that's what you're achieving. The fourth partial sum will come out to a specific number. Whereas the sequences, remember, we had a list of numbers. So this one is just the sum will be one specific value. Now sometimes when we do sums, we denote them a certain way, and we use something called sigma notation or summation notation. And this uses the Greek sigma symbol. If you notice, it kind of looks like an E, but it has little legs here on the inside. I had a college professor that got very particular if I didn't have sharp corners here and didn't draw my sigmas correctly. But let's talk about some of the parts. You will have a value up here at the top. That will be the upper bound. For example, up here we went up to 4, the fourth term, so that would have been a 4 there. The lower bound will tell you where you're going to start. Usually you start at 1. Occasionally it's at 0. and even more rare would be somewhere else. It's usually at 0 or 1. The value here can be any letter, and that is the index of summation, but that value is going to be what is in the equation. So here, if I am substituting 1 for n, and then 2 for n, and then 3 for n, that is the index. And if you notice, as I go all the way up to whatever value this is, the upper bound, that is the last value that I am substituting in. So my last number in the sequence is a sub k. And then to get the series, the sum, you would just simply add up all those terms. So this can be done very neatly. There is a way to do this on the calculator, but as we've talked about before, it's sometimes very easy just to plug the values in and sum them up yourself. We will want to see you using these equations and writing out the terms, so you'll still need to know the equations and practice doing that when we do these examples and on the assessments. Let's go ahead and try an example. If we have, let me pull this out here, if we have, example 7 is the summation of from 1 to 5 of n squared minus 1 over 2. So when we plug that in, let me get some paper underneath here. It'll show up a little bit better. There we go. If I plug in 1, I'm going to have 1 minus 1 over 2 plus. I'm just going to go ahead and plug in the values. I plug in 2, I'm going to have 2 squared minus 1 over 2. 3 squared minus 1 over 2. 4 squared minus 1 over 2. 5 squared minus 1 over 2. Now I stop at 5 because that is my upper bound. And then you just simply get the values. So that would be 0 over 2, that's usually 0. That would be 4 minus 1 is 3 over 2. This would be 9 minus 1, that would be 8 over 2, which is 4. That would be 16 minus 1, which would be 15 over 2. 25 minus 1, which would be 24 over 2. And then you simply add those up. And you add that up and you see it comes to a nice, neat 25. Again, the sum is going to be a nice number, not a series of values that you're adding up. I want you to actually add up the sequence and give me the sum for the series. All right, now, if you'll notice, this one went to 5. This is a finite series. This would be an infinite one. You say, well, Ms. Reams, how can I go to infinity? How am I going to know what's happening? All right, well, let's look at the pattern. If I plug in 1 here, that's going to give me 6 over 10. Plus, if I plug in 2, that's going to give me 6 over 100. If I plug in 3, I think you get the idea, 6 over 1,000. Let's do one more. 6 over 10,000. And I'm just going to put dot, 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 because I know it keeps on going. Well, let's look at what these values are. That is 0.6 plus 0.06 plus 0.006 plus 0.0006. Do you see what's happening? So if I went to infinity, I would end up with 0.666666666, correct? That is the value we know as 2/3. So that sum, that series, will give us 2/3. And it would go to infinity. You can have as many 6s as you want. Okay, 0.33333333 forever would still give you 1/3. Right? So we're going to play with this when you come to class. We are going to, you're going to give me some of the numbers in the series. You're going to figure out the patterns. You're going to tell me convergent and divergent, and you're going to use the sigma notation for some of these. And I will see you then when you come. Thank you.